Hi everyone, I am Yashash. This is Sreekanth. We are software engineers. We build Numaflow platform at Intuit. Today we'll be talking about how we streamlined AML inference workflows on K8s using our platform. The agenda for today's talk is going to be, we'll talk a little bit about Intuit, what we do at Intuit, what's the technology at Intuit looks like, and what's the scale at which we operate. And then we'll talk what exactly we mean by inference on streaming data, and what are some of the challenges that were faced by the ML teams, and how we've solved those challenges using our platform. And finally, we'll do a live demo. So this is what technology at Intuit looks like. We have multiple products across Intuit to call out TurboTax, Credit Karma, QuickBooks, MailChimp. So we have close to 100 million customers across all these products. And we do 100 plus in consumer tax refunds every year. And 2 trillion plus invoices are managed using our platform. And almost 18 million US workers are paid using QB payroll platform. So I want to emphasize more on the scale at which we operate. So the solutions and the platforms that we build has to be highly available and scalable to support this scale. We are also strong believers in open source. We have got End User Award in 2019 and 2022. And we also contribute to open source. We are creators of Argo and Numaflow. And we also maintain those projects. At the same time, we are also active users of end users of a lot of Kubernetes, open source technologies, both in cloud and mobile. To call out, most of our workloads at Intuit run on Kubernetes. So what exactly, let me talk about inference on streaming data. So before I talk about it, I just want to give a quick overview about our AI native development platform. So we run more than 4 million models in production every day, and almost 60 billion plus machine learning predictions happen using our platform, and almost 40 million AIOps inferences are done using our platform every single day. So this emphasizes more on the scale for our at which we use AI at Intuit. So this is the high-level architecture of how the inference of streaming data looks like. It's all about reading data from an unbounded stream. It could be coming from Kafka, Pulsar, or SQS. A stream could be like a clickstream event or user activity across our Intuit products. So, and we read these events and do some pre-processing or filtering, or let's say we want to add more fields to that event. We can do that in the pre-processing step. And in the next step, we do the inferencing. And once the inferencing is done, we could write it to DB or use that inference data to do some decision making or some analysis, or we can write it to another stream where we can do further processing. So let's look at some of the real world examples. The first one is we can use it for e-commerce real-time recommendation. Let's say we have, based on how the customer interacts in the website, we suggest them appropriate products. The second would be for IoT predictive maintenance, where we have sensor data that is coming as a form of stream, and we do on-the-fly anomaly detection to determine whether there is a potential failure or there is any device failures. Or we could also use for real-time analytics, where we have continuous stream of data, and we continuously analyze it and use it for doing something like dynamic pricing, orders, etc. And we could also use it for fraud detection, where if you have a transaction stream coming and you want to determine whether it's a valid transaction or not. So stream processing being one of the backbone of modern technologies, let's look at some of the challenges that were faced by our ML teams that made us build this platform. The first and foremost challenge is the stream processing is tightly tied to data engineering. So if you have to do stream processing, engineers had to learn a lot of JVM-based technologies and big data systems to really get into it. And ML engineers, they want to do a simple processing using tools that they are familiar with, and they don't want to learn these big data systems. So this was the major challenge that we saw. The second challenge was they had to write a lot of boilerplate code. When I say boilerplate code, let's say you want to consume messages from Kafka, you have to write that Kafka consumer, the polling logic, hacking logic, all these things, the ML engineers had to do it. And they love to do the ML stuff, and instead of writing the business logic, they were spending too much time on the integration and writing the consumers. The third and the important challenge we faced was the scaling complexities. Since the ML workflows can be super slow, doing a high number of messages per second was like a very big challenge. Most of the times, engineers had to do a lot of fine-tuning, and also ML workloads needs to be scheduled on GPUs, which was another big issue. And for them, they were spending too much time on managing the infrastructure and setting up the whole infrastructure, and they were not able to ship the products faster. So now let's see what exactly is Numaflow. So the way we define Numaflow is as a serverless platform to do stream processing. What and all we solved, right? So the first important thing is we abstract out the infrastructure. So we enabled ML engineers to do stream processing faster by completely abstracting the infrastructure so that they can only focus on writing the business logic. And us being the platform, we will take care of all the infrastructure and manage it. The second is we decoupled the ML logic from the sources and sinks. So we decoupled the processing logic. So now they don't care whether the payload is coming from Kafka, SQS, or Pulsar. For them, they only care about what the payload is, but they don't care about where it's coming from. So irrespective of the sources and sink, since we decoupled it, irrespective of source and sink, whatever the logic they write, it should work. The third important thing is we fix the scalability and reliability issues. So now using the platform, we give out-of-the-box auto-scaling support, and the auto-scaling is not just based on the HPA or the CPU and memory. We look at how many messages are pending, what's the processing rate, and what's the consumer lag. Based on that, we auto-scale so that there is no end-to-end latency. And if there are like sudden spikes in the traffic, the platform should be able to handle such spikes, and users don't have to fine-tune the system. Now, let's look at how the streaming inference using Numaflow looks like. The first important step is we have a source where we will be reading messages from. A source could be anything. Most of the time, a platform provides out-of-the-box connectors for sources and sinks, so users don't have to write any code. All they have to give is the topic name or the broker details and connectivity. It's mostly config-driven. And then the main code part they have to do is write a simple UDF. We call it as a user-defined function. They have to write the logic of what they have to do once they got the event. So that will be present. That logic will be present in the UDF. And in the UDF, it could be a simple map operation, or it could be a flat map operation where one request can be split into multiple responses. Since the ML inferences can be slow, at the same time, they can do streaming as well to give real-time updates about how the inference is performing. There is a concept of map streaming. We'll cover it. And then we can also do conditional forwarding. So our platform supports out-of-the-box conditional forwarding. Users don't have to do anything for that. Like based on some conditions, platform will decide where to send that message, which UDS to forward that message. That is provided out of the box. At the end, now that we have processed the messages, we have to persist to the sink. Even for sink, we provide most of the connectors, so users don't have to write anything. At the same time, if you want to write a custom sink, where, for example, if you write to a PostgreSDB or a blob store, you could implement that, or you can write it to a stream where it can be further processed. So, with this, I would like to hand it over to Sreekanth to do a live demo. I covered a lot of concepts. With a live demo, it will be easy for all of you to relate to those concepts. Over to you, Sreekanth.
Thank you, Yashash, for the quick introduction about Numaflow. In this demo, I'll be showing an image recognition pipeline. The pipeline has a source through which we'll be receiving events. In this case, the event payload being the images. OK. And within the second step, we'll be doing prediction. The prediction here means like identifying what is the content of the image and generating a summary of the description of the image. I'm running an LLM model that I downloaded from Hugging Face in this case. And then this description will be forwarded to the sync stage. Let's see how it works. So I have a photo of Sachin Tendulkar, and I'll be sending OK, 1 second, I need to show. For the source, I'm using HTTP source. You can use any other source like Kafka, Pulsar, SQS. These are built in within the platform. And for sync, I'll be using log sync, which will basically print the description to the console. So the HTTP source will allow me to inject the image to the pipeline using HTTP clients like curl or Postman. So yeah. So this is the image that I'm planning to send. Okay. One second, let me check the port forwarding. Okay. Sorry, there seems to be some connection issues. So this is what the pipeline will look like. I had sent images like earlier when testing this thing. I hope it shows here. Yeah. So basically, it will show the description like a cricket player in blue uniform is in the middle of a shot with the crowd in the background. So Numaflow comes with a built-in web UI. This is that UI. Each step in the processing logic is called a vertex. And each vertex, this is the boxes that you see here are the vertices. And each vertex internally runs a number of pods. Here, each one of them is running only one pod. And if you click on any one of the vertex, you can see more observability metrics like CPU memory usage, the logs, and also this application-specific like processing-related metrics like read latency, write latency, all that data will be shown here. Okay, now let's go back to the slides. So now let's see how we can build such a pipeline. So we have a custom resource called a pipeline, which has two major components. One is the list of vertices, and the second part is the list of edges. So the list of vertices is, in this case, the data is coming through an HTTP source, and this data is forwarded to the image recognition vertex, where it will be running a user-defined function within this container. And the output of that is forwarded to the logsing. The HTTP and log, in this case, is built-in sources. So there is no need to provide a container image. And then within the edges is this dotted line that is shown. This describes the direction in which the data flows within the pipeline. So within the edges specification, I am specifying the data should flow from HTTP source to the image recognition step, and then from there to the log vertex. This is one of the vertex that was shown in the previous slide. If you have the need, you have the option to specify more settings like the node selector. In this case, it has a LLM running, so LLM is hosted within the container itself. So I am specifying the node selector to ensure this pod is scheduled on GPU nodes. And then I'm also specifying resource requests and limits. I also have the option to specify the scale, the min and maximum number of pods that each vertex should spin up. Because the scaling happens at each vertex, depending on how many messages are in the queue for that specific vertex. So let's take a look at how the user-defined function will be implemented. We support 5 languages as of now. Those are Python, Java, Rust, Go, and TypeScript. This example, I'm showing Python. So we expect the user to implement one handler function. This is the signature of that function. It will take a datum object, and you can extract the actual payload of the payload data that is coming to this vertex from the previous vertex using the attributes and methods available on this object. In this case, I know the payload that is coming to the vertex. This vertex is an image. So I use the respective libraries to treat it parse it as an image. And then I'll be doing my processing, in this case, sending it to an LLM and generating the description of the image. And then I return this description. So this is all it takes to implement a user-defined function. Now let's see like a slightly more complex example. In this case, I can show the yeah. I have a fraud detection pipeline. In this case, the events are coming through both Pulsar and Kafka. So some of the events that are coming through Pulsar might be missing some of the fields. So that enrichment is done at the preprocessor stage. And both of this data is sent to the fraud detection step. And the output of the fraud detection is sent to a Postgres sink, where I'll be saving the results to a database. And the Kafka sink, and also the data is sent to a Kafka sink, where the data will be forwarded to another Kafka topic. Some other team might be listening on that topic. The Kafka sink here is provided out of the box, but Postgres, saving to Postgres, I'll be implementing myself. I'll show the function signature there. Now let's go back to the slides. Okay. So this is how the payload look like that is coming through both Pulsar and Kafka source. The fields or the details are not important. The only thing is this is JSON data. So in this case, there are two sources. And since these are built in, I only need to specify the broker URL, the topic name for both Kafka and Pulsar. And the platform will ensure the events are available within the pipeline. So this is how the fraud detection implementation looks like. So if you look at this function signature, it's exactly same as the image recognition implementation in terms of the function signature. So, but the only difference is that in this case, I know the payload that is coming from my previous vertex, that is the source, is in JSON format. So I'll be treating it as JSON and parsing it. Then I'll be doing my processing, which is like predicting whether it is fraud or not. And again, I'm converting it back to JSON and then forwarding the message to the next vertex. So as you can see here, it doesn't say whether the data is coming from Pulsar or Kafka. We only need to write the processing logic. User doesn't have to worry whether it is coming from, which source the data is coming from, basically. And this is the Postgres sink. This is where the data will be saved to the Postgres database. In this case, the method signature is slightly different. So here I'm taking a list of, here you have to take a list of datum objects. And then for each object, I know the datum that is coming from the fraud detection stage is in JSON format. So I pass it as JSON, then I save to DB. And then I return a special message saying that processing for this specific message is successful. So as you can see, Numaflow provides, is more like a serverless platform that abstracts all the complexities with the stream processing. I also want to quickly show one of the pipeline that we are running in production. So this pipeline does anomaly detection. So within this pipeline, there is a pre-processing stage. Is it visible? There is a pre-processing stage, and after the pre-processing, some of the data is sent to trigger training workloads, and some of the data is sent to the inference stage, and yeah, there is a post-processing stage and so on. So as you can see here, this pre-processing stage runs only 2 pods, but the trainer vertex is running 23 pods. So each one of this vertex is scaled independently based on how much data is in its queue to process. Okay. So these are some of our community users. The project is open source. So Intuit uses it for anomaly detection and other stream event processing use cases. NTT uses it for accelerator chaining, and Lockheed Martin uses it for IoT data processing. And Valega Chain uses it for fraud detection on blockchain. So the platform is diverse to cater like different use cases. Yeah, with that, yeah, the project is open source. You can check out the project here. And yeah, we are open for questions.